All right, our next topic to discuss here is color and vision. When we look at the eye, it appears that there's two kinds of receptors. There's rods and cones in the back of the eye on the retina. The rod cells are simply able to perceive light and dark, so essentially like a black and white sort of sensation, whereas the cone cells are able to perceive color. Now, in closer look, it appears like the cone cells have the ability to distinguish between three main colors. There's really a range of wavelengths that these three different types of cones are able to perceive. So we typically think of one part of the cone able to receive blue, one kind of cone able to receive green, and one kind able to receive red. But as you notice, there's really this concept of an overlap, but we typically just say that our eyes are able to perceive red, green, and blue light, or a blend of those things. Now, this really leads to how we perceive light. Now, if you think about it this way, what we see is 100% based on light that enters our eyes. So that sets up kind of three big categories: black, color, and white. Now, black's an easy one. Black is no light at all. And what we typically call black in day-to-day experience isn't truly black, it's more of a gray. This video here reveals what's really close to black.
A high-tech company by the name of Surrey Nanosystems claims to have invented the blackest black you have ever seen, which goes by the name of Vantablack. Vantablack is the definition of darkness. It's a material that absorbs 99.965% of ultraviolet, visible, and infrared light. This super black coating holds the Guinness World Record as the darkest man-made substance. To give you an idea of what that actually looks like,
what you just saw as clearly a three-dimensional mask, we're just seeing as a shadow, a void. We can't make out any different detail here because it's truly reflecting no light to our eyes. And so this void is black. And even the video is not going to convey truly what black is, because there's going to be some amount of light coming from that black zone. You'd have to be there in real life to truly perceive it. But I think it gets the idea across quite nicely. Now, when it comes to color, what we perceive as color really comes from a blending of the three main light colors. So in this cool interactive from CU Boulder, you notice that there's this idea of this person who really is going to perceive something through their eyes, and that's going to send signals to the brain for us to perceive in these little bubbles you see here. So if we add some red light, which is shown as little photons, then the brain perceives an increasing intensity of red. Lots of red gives us the bright, strong red. And we'll see the same thing as we run down through these others. If you see green, nice strong green. If we jump down to the blue, we'll see a nice strong blue. Now remember that this is light entering our eye. We're having a perception of light. So now let's add a little mixture. Let's add red and green together. Our brain perceives yellow. So the primary color of red and the primary color of green, when mixed, makes your brain see yellow. Red and blue light together makes you see magenta. Again, we're focused on light entering your eye. And if we have a mixture of green and blue light, then we see the secondary color we call cyan. As a reminder, like we talked about, black is simply what you perceive when no light is entering your eye. Now, if we turn on all three at full blast, your brain perceives white. This is rather weird, but when an equal intense amount of red, green, and blue enters your eyes, your brain perceives that as white light. So the lights in your room, the sun, we typically think of that as white light, is really a mixture of all these colors. And you'll notice that as we adjust the sliders to different slight amounts of each color, you can get the entire spectrum of different colors that are possible to perceive with our human eyesight. So this diagram really reveals the primary colors of light. You see red, green, and blue around the outside, those being the primary colors. And when you have a mix of colors, you get the secondary colors. And if you perceive all three at the same time, your brain perceives white. Weird. Now that we understand how our eyes perceive color a little better, let's look at how that affects how we perceive surfaces and how pigments play into that. When we start to consider the color of a surface, you have to really think about two things: the light hitting it, and then what the surface does to that. So let's look at that a little bit closer here. Okay, what we're going to look at here is how light and surfaces cause the color we see to be what it is. We have a little location that under white light, like you're seeing it now, is red. So we call this a red surface, and the reason why is because it reflects red light. In other words, if we shine white light on the red surface, it reflects only red. Now remember that white light is actually red, green, and blue. So it's a combination of red light, blue light, and green light all at once. That's white light, regular light like you see from this lamp here. Why does this surface appear red? Simply because it reflects the red light, and that's what we see. What happens to the green and the blue light? It's simply absorbed by the surface due to the chemistry of whatever molecular structure is there. It just absorbs the green and the blue and reflects the red. Now, where things get more complicated is what would something look like under different light? What if we shine cyan light on a red surface? Well, cyan is blue and green together. Blue and green light. Well, what's going to reflect? Nothing. We just saw that blue and green are absorbed. There is no red there to reflect. And if nothing is reflected, then we would see black. So what we would typically call a red surface would appear black under cyan light. And we could even extend that and say it would also appear black under blue light or green light, because if there's no red light present, there's nothing to reflect. Now, for our eyes, that means that it has the ability to reflect both red and green. Red and green together, when it hits our eyes, gives us the sensation of yellow, or the perception of yellow. So we could really say that a yellow surface absorbs blue and reflects red and green. That's why it appears yellow under white light. But what if we only shine red light on the yellow surface? So the red is reflected. What do we see? We see it as red. We don't see it as yellow anymore because there's no green light there to reflect off. There's only red light. So we would no longer call this a yellow surface because we can't tell. If we're only shining red light on it, it would appear red. What if we shine cyan light on this yellow surface? It's going to reflect the green and absorb the blue, just like it always does. That means we're going to see this yellow surface as green, no longer yellow. Very interesting. Now, this color wheel kind of highlights this idea, but takes it a little farther in the concept of how do you mix pigments in order to get another color. Pigments have primary colors as well. Most of you, if you've done some art, would think of it as red, blue, and yellow, but it's truly magenta, cyan, and yellow. Now let's look at why. If you think about a surface or a pigment, a paint we could say, that we call cyan, the reason that a pigment appears cyan is because it reflects green and blue and absorbs red. If we think about a pigment that is yellow, the reason it's yellow is because it reflects green and red and absorbs blue. So, if you were to mix cyan with yellow, cyan absorbs red yellow absorbs blue, so the resulting of mixing cyan and yellow is going to be green. It's kind of weird when you think about mixing pigments, or if we want to call it paint. It's really, you have to think about what is absorbed by each and then what is left over to be reflected by the combination. If we mix cyan, yellow, and magenta all together as pigments, then no color would be reflected if you shone light on it because they would be absorbing everything. If you look in your printer, the ink in your printers are cyan, yellow, and magenta, and then along with a black pigment to make a really strong black. All right, some other vision concepts here are mirrors, lenses, and vision. Again, we talked about this with color, but it still is super important to really think what we see is completely defined by the light that enters our eyes. It's 100% based on that. But light can be altered on the way to your eyes by mirrors and lenses, causing images to be different than reality. So let's take a look at mirrors first. When it comes to vision, sometimes our eyes can even deceive us. Because what just might seem like me talking to you, and then you wonder, like, wait a minute, how come Sam points backwards? When I give you a little bit bigger picture of what's going on here, you realize that it's actually me talking to you in the mirror, right? That it's a mirrored image of me. But when you think about this, this is rather strange because if you look at it, it looks like somehow I'm on the other side of that wall. And when I hold up this hand and it looks like I may be waving to you with my right hand, this is actually my left hand that I'm holding up in order to make it appear this way. So what's going on with the light coming off of me in order to make it look like this for you and honestly for me too? What we see is completely based on what light enters our eyes. So imagine light from an object hitting a mirror and reflecting like so. The light that enters your eyes seems to have come from this spot behind the mirror, so that's where you see it. The same concept applies to curved mirrors. The light from an object reflected off that curved mirror follows certain rules. Now, if that light enters your eye doesn't know what's happened to it along the way, so your eye thinks that the object is really in this location. There are other types of mirrors that essentially work the same way. Now, lenses are another way that light can be altered. In this diagram, you'll notice light coming from an object traveling through a lens, again following certain rules, but due to the way the light is altered and then perceived by the eye, the image looks different than it really is. Now let's look at an interactive that allows us to see this in action. See that we have a lens here and a candle acting as a source of light. Now we're going to adjust the height of this candle just so you can focus on what we're seeing here. Notice the rays of light traveling through the lens, creating the image on the right. Now as you move the object, the way those rays of light travel through the lens is changed, and so the image of the candle is altered as well. There's some rules that are followed. The parallel ray goes through the focal point, and a ray through the focal point comes out parallel. Those are some simple rules there. The rules are the same if you look at a mirror. Again, moving that source of light alters where the image is, even though the rules are the same. Parallel light goes through the focal point, and light through the focal point comes out parallel. You can even have the image appear to be behind the mirror and enlarged. Again, it's all about where your eye thinks the light is coming from in order to define the image you see. There's also a concave or diverging lens here. Similar idea that we've been saying, rays of light follow rules, and that causes the image to appear where it does. Okay, one final thing to take a look at is some cool tricks here. This first one has to do with what's called retinal fatigue. Now, you probably have already seen the effect happening, but if you stare at the very center white dot very intently without moving your eyes, and then allow your eyes to kind of dart around a little bit, you should notice that the white dots seem like they're flashing, but if you stop and stare at any one of them, they really aren't. It's that those white dots are essentially searing into your retina, a place that's lots of white light, and then the black squares are places where no light is. And as you make tiny little micro movements of your eye, the white gets overlaid by what was black, and that like after image kind of gets carried. And so you see what seems to be like flashing dots, even though it's not really flashing. You'll see a similar effect here, though we bring the color aspect. As this missing pink dot zooms around in a circle, what you perceive is what seems like a green dot. And it really has to do with your eyes getting fatigued or tired of the magenta. What's missing from magenta is green. So your eyes get tired of seeing the red and the blue. And so when that goes away, you perceive a flash of green. Though there's not really a flash of green, it's just a space where there is no pink zipping around in a circle. It's pretty awesome. So hopefully that brings together lots of different pieces of color and vision and how we see. Of course, there's more, but that was scratching the surface of all the little tidbits. Hopefully it puts some pieces together for you and you feel like you get it a little better.